Physics Part 194. So if an electron absorbs enough energy, it should be able to escape from the metal. Remember from chapter 8 that the energy carried by a wave depends on its amplitude and its frequency. Thus, even if we have a low frequency wave, its energy can be boosted by increasing the amplitude, that is, by increasing the brightness of the light. So according to wave theory, we ought to be able to cause photo emission by using any frequency of light, provided we make it bright enough. Alternatively, we could use less bright light and shine it on the metal for a longer time until enough energy to cause emission has been delivered. But this does not happen. The experiments we have described above showed conclusively that radiation of frequency below the threshold, no matter how intense or for how long it is used, does not produce photoelectrons. The classical wave theory of electromagnetic radiation leads to the following predictions. Number one, whether an electron is emitted or not should depend on the power of the incident wave, that is, on its intensity. A very intense wave of any frequency should cause photo emission. Number two, the maximum kinetic energy of photoelectrons should be greater if the radiation intensity is greater. There is no reason why photo emission should be instantaneous. These predictions based on wave theory do not match the observations. A new approach based on an entirely new concept, the quantum theory, was used to explain these findings. Einstein's theory of photoelectric emission. In 1901, the German physicist Max Planck had suggested that energy carried by electromagnetic radiation might exist as discrete packets called quanta. The energy E carried in each quantum is given by E is equal to hf, where f is the frequency of the radiation and h is a constant called Planck constant. The value of the Planck constant is 6.63 into 10 to the power raised to minus 34 joules per second. In 1905, Albert Einstein developed the theory of quantized energy to explain all the observations associated with photoelectric emission. He proposed that light radiation consists of a stream of energy packets called photons. A photon is the special name given to a quantum of energy when the energy is in the form of electromagnetic radiation. When a photon interacts with an electron, it transfers all its energy to the electron. It is only possible for a single photon to interact with a single electron. The photon cannot share its energy between several electrons. This transfer of energy is instantaneous. The photon theory of photoelectric emission is as follows. If the frequency of the incident radiation is less than the threshold frequency of the metal, the energy carried by each photon is insufficient for an electron to escape the surface of the metal. If the photon energy is insufficient for an electron to escape, it is converted to thermal energy in the metal. The minimum amount of energy necessary for an electron to escape from the surface is called work function energy. Some values for the work function energy and the threshold frequency S0 of different metals are given in the table. Sodium, calcium, zinc, silver, platinum. And they are 3.8 into 10 to the power raised to minus 19 for sodium, 4.6 into 10 to the power raised to minus 19 for calcium, 5.8 into 10 to the power raised to 19 for zinc, 6.8 into 10 to the power raised to minus 19 for silver, 9.0 into 10 to the power raised to minus 19 for platinum. Well, Sodium it's 2.4.